Hi, I'm Gaurav. I present our work, the crop, data-efficient certified robustness for pre-trained classifiers. In certified defense, the model predictions on the neighborhood region lying within wall of small radius around the input sample is guaranteed to not vary and remain constant. There are several techniques for certification, but randomized smoothing is the most popular one, as it does not have any architectural dependency, and thus scalable to deep neural networks. For certification with randomized smoothing, Gaussian perturbed copies are fed to base classifier BC, which predicts C1 as a most probable class with probability P1, and C2 as runner-up class with probability P2, then smooth classifier SC is provably robust around input, within the certified radius RC. However, it is impossible to exactly calculate P1 and P2 when BC is a deep neural network. Cohen et al. Use Monte Carlo technique to estimate lower bound on P1, and upper bound on P2. The certified radius RC is directly proportional to P1 bar. This implies that for higher RC, the base classifier should predict the most probable class as the correct class with high probability. However, any off-the-shelf classifier is not robust to the input corrupted by Gaussian noise, leading to low P1 bar and poor certification. Also, training from scratch on Gaussian noise augmentation is not a viable option, especially when large pre-trained models are shared as an API. To avoid this, Salman et al. Proposed the denoised smoothing technique where a custom-trained denoiser is prepended before the pre-trained classifier, but they use the entire training data for training denoiser. However, the API provider may only provide access to only a few training samples due to heavy transmission costs or proprietary reasons. In such cases, when we perform denoised smoothing directly, the certified accuracy decreases significantly as the number of training samples reduces. Thus, our objective is to improve the certified robustness of pre-trained models in limited data settings. We observe that using different conventional approaches such as explicit regularization and data augmentation only lead to a marginal improvement in performance. We overcome this limitation, and propose a novel sample generation strategy that synthesizes boundary and interpolated samples to augment the limited training data, as shown in Thiessen plot. Our generated samples increases the feature diversity of limited original training data. We synthesize these samples in stage 1. Since adversarial samples flip a classifier's prediction while preserving the semantic content, they serve as a good candidate for a proxy of class boundary samples. Next, we obtain interpolated features by performing a mix-up between the features of generated boundary sample, XIB, and original training sample, XIO. Then, we craft the input sample corresponding to the interpolated feature by perturbing the original sample to match its feature response to logit time, using mean square error laws. In stage 2, a denoiser network DN is attached before the pre-trained base classifier BC. Also, we add a domain discriminator network DD along with gradient reversal layer. To ensure label consistency, we use cross-entropy loss to ensure that the label predicted by the pre-trained network BC on original clean data and denoised output of its Gaussian perturbed counterpart are same. To enforce sample-level feature similarity, we apply cosine similarity loss between logit features of denoised output of our generated data, and features of limited training samples. To enforce distribution-level feature similarity, we use MMP loss between set of our denoised generated data and set of limited training data, at normalized pre-logit layer of BC network. We also train domain discriminator network DD using binary cross-entropy loss to distinguish the distribution of Gaussian perturbed samples and clean samples. The negative gradients are back-propagated via GRL, helps denoiser network to learn domain invariant features. Hence, the total loss in stage 2 is a combination of these 4 losses. We evaluate the efficacy of our generated data and observe that, using both boundary and interpolated samples leads to a massive improvement in performance over the baseline. Enforcing distribution alignment using discriminator yields more gains in performance. Moreover, further applying MMP loss yields significant improvements on both standard and robust accuracies, across radii. On different datasets like C410 and many ImageNet, our method to crop performs much better than the existing approaches. We also extend our approach to black box scenarios where we observe minimal drop in performance, compared to white box setting. Our method, the crop, obtains significant gains in certified performance across different budgets of training data. To conclude, we proposed for the first time a certified defense for pre-trained classifiers in limited data setup. The method contains 2-step process and we extensively validated its effectiveness across both white box and black box scenarios.